It is going to be a little tough to get back to center after that. That was just fabulous. All of these talks this morning have been so moving. And I really love this group. Okay, so I get to talk about the EUGENE Shoemaker Distinguished Scientist Medal. And I'm going to preface this by saying that my remarks are going to be a lot shorter this year than they normally are, because I was duped into this. All the rest of them told me we were going to make things really short, so I made mine really short, and then they made theirs a lot longer. So please don't take this to mean that I think any less of either of the people I'm talking about. I'm just trying to do what I was told. Okay. All right, so CERVI's, as you know, CERVI's most distinguished award, the EUGENE Shoemaker Distinguished Scientist Medal, was named after one of the founders of planetary science, EUGENE Shoemaker, who passed away in 1997, far too soon, and he was somebody who inspired so many of us in this room and continues to do so. He was one of the pioneers of lunar and planetary geoscience, and he really inspired a generation of researchers studying the solar system. So CERVI proudly presents the 2018 Shoemaker Medal to Dr. Darby Dyar this year. Darby is professor and chair of the Department of Astronomy at Mount Holyoke College, and she's had a very distinguished career already. She is the author of at least 242 peer-reviewed papers so far. Darby's expertise spans many subjects, including optical mineralogy, crystal chemistry, and numerous spectroscopic techniques. As you can see from the earlier images that were shown, she has, just impacted so many young people and peer colleagues alike. In recent years, she's also revolutionized the use of machine learning techniques in the analysis and interpretation of X-ray absorption spectra. Her careful laboratory, this is a quote I'm going to read you now from someone who nominated her. Her careful laboratory work and model development have enabled thousands of other papers that use data she generated. Her work will prove to be substantially more important than any single mission. That's an incredible statement. She has won several prestigious awards, including the 2016 Gilbert Prize from the Geological Society of America. But knowing Darby, I think the following comments mean even more to her. Multiple colleagues have said of Darby, she is generous of spirit, and with her as a she is generous of spirit, and with her time as a scientific collaborator, mentor, and friend. And they've also added that she has so many active collaborations, and that is no accident. Her expertise in numerous areas is widely sought after, and she provides not just data and input, but careful thought, deep understanding, welcome advice, and for those of us lucky enough, friendship. We at CERVI appreciate the significant scientific contributions she has made throughout the course of her career and the mentorship she has provided to so many. It is our extreme pleasure to present her with this year's EUGENE Shoemaker Distinguished Science Medal. Would you please join me in welcoming and congratulating Dr. Darby Dyar.
Did you load my talk? Yeah. Please tell me that you did. Oh, excellent. Well, I want to start out by saying how incredibly honored I am to get this award. As a young graduate student one summer, I drove from Boston to Los Angeles to work for an oil company for a summer. And it was the first time I'd ever been paid to drive anywhere. And among other things, I stopped at the Grand Canyon, spent the night in a hotel, which was only the second time in my life I'd ever been in a hotel. But the next morning on my way, continuing west, I pulled off the highway and looked at Shoemaker Crater. And I remember thinking how incredibly holistic this guy is, that he can look at a hole in the ground and as a geologist visualize where it came from. I was so impressed, and then I, of course, subsequently got to meet him. So it's a true honor for me to receive this award. And I also want to thank the Surveys, of which I am part of many of them. All right, so my remarks, for those of you who know me, will not be a surprise. I'm going to talk a little bit about myself, a little bit about science, and try to take advantage of this as a sort of a teaching moment. All right, so how do I advance this? This? No? It's the big button. Press the big button, Darby. Okay. Of course, I have to start out by saying that when you get this award, you look at all the other previous people's speeches, which are all streamable online. And I have to say that I can't write a poem like Carly does, nor can I name drop like Jim Head, and I certainly don't have the sense of humor of Jeff Taylor. But I can talk about people, and I think I do have some talents in that direction. These are the two most important people in my life, my son Duncan and my daughter Lindy. I am good at a few things that don't involve poetry. I'm a quilt maker. This is a quilt that I made for Brad Thompson and Molly McCanta. It has planets on it, as you can see. I'm also not a bad rower. That's me in the front, stroking. Yeah, there we go. If you're a rower, you would know what that means. Let's see. But this is probably my most comfortable and valued role in my life, which is that one of a teacher. And so I'm going to use the rest of this talk to make it a teachable moment for all of you. I can't resist the opportunity to show a few cute pictures of me as a kid. This is me with my brother Hunter. I grew up in the Midwest in Indiana, and unlike 95% of the people in this room, I did not want to be a scientist. I hated science. Whenever science or math came up in a classroom, I blacked out. I was terrible at it. And Indiana did its best in the 1960s to convince me that women didn't do science or math and that I would be terrible at it. So for me, the path to where I'm standing here right now was perhaps different from that of many of the people in this room. Let's see. All right. Okay, I'm pressing the button. Okay, there we go. I wasn't the greatest of students either. I got a series of probably every single report card I got until 9th grade said I did not talk at the proper time, and that I had trouble sitting still and focusing. I still have trouble with all these things. But I think I've gotten better at managing them, let's put it that way. There we go. So being of this Hoosier bent, I arrived at college thinking that I would study art, and indeed I did study art. I went to Wellesley College. I was the third generation of my family to go to Wellesley, and I decided I would study art and art history. I was inspired by both my parents. My father down there in the bottom worked for General Motors for 35 years in a plant in Indianapolis, but he had the good fortune of working on the Apollo landers, so I did have a little bit of stake in planetary science, even from birth. My mother was a preschool teacher for many years, and she was also very inspirational. When she was 48 years old, she decided she would go back and get a PhD, which she did. So she got her PhD the same year I got my undergraduate degree. And if that isn't inspirational, I don't know what is. But I had a lot of other really inspirational people in my life because obviously I had to get from there to here. And probably the thing that made my life change was the fact that Wellesley College has a science requirement. And I tried to ignore the fact that this existed until some point in my sophomore year when I met with my advisor, and she said, you do know, Darby, that you have to take a science course to graduate. And I said, oh no, please no. I'm really bad at science, Meg. And she said, well, no, you have to do this. You can't get around this requirement. So I asked around to find out what the easiest science course was. And of course, it was Rocks for Jocks. And so I reluctantly signed up for Rocks for Jocks, slithered into the back row of the classroom, and met this woman in the upper left, Meg Thompson. Meg was fresh out of Harvard at that time. She was a field geologist, and she showed in this first lecture a bunch of slides, and I had light bulbs go off in my head at every slide. And I thought, oh, that's a woman and a scientist. I've never seen one of those people before. And look, she's talking about stuff that I actually understand. So Meg convinced me that I should double major in geology and art history. And so this is me in the lower left here. That T-shirt says igneous is bliss. I did subsequently work for an oil company. I went to field camp and then subsequently taught field camp. So I thought I was on a path to go become a field geologist until fate intervened once again. At the beginning of my senior year, I ran out of money because I had been at field camp the previous summer and I had no money. So I started asking around trying to find a job. And one of my professors at Wellesley had gone to MIT. And this person said, go talk to this guy, Roger Burns at MIT. He likes to hire undergrads. You'll be happy there, Darby. So I made an appointment with him, and I dressed up, and I went nervously to MIT, and I timidly knocked on his door, and I walked in, and I said, I'm here to meet Professor Burns. And he said, oh, it's just Roger here. I went, what? And he proceeded to hire me, and I guess my history was changed then and there. Roger Burns, many of you won't know this, but he is the author of really the penultimate book in mineral spectroscopy, which is called Mineralogical Applications of Crystal Field Theory. And of course, Burns Cliff on Mars is named after Roger. So that's the Mossbauer spectrometer behind him. That's what I learned to do when I was at MIT. However, the reason he hired me actually had to do with computers. So in those days, there was only one computer science course at Wellesley College. This tells you what a dinosaur I am. And I had taken it. So I was skilled in computing because of that. And so when Roger hired me, what he wanted me to do was to convert his software from, believe it or not, from these cards here, these paper cards, to paper tape, which is shown in that lovely teletype machine. And then I managed to rewire this thing to connect it to his spectrometer, because poor Roger, when MIT moved on from mainframes and cards, he didn't have any way of getting his data. So I did that. I bought a new computer for him. I showed him how to make plots of his own. And I used this spectrometer in the upper left, which many people in this room have used. This was state of the art in 1977. It's called a Carey 17 spectrophotometer. And I remember standing there watching the light change, because you could, it was all open. You could see the color of the light change. And I thought, oh, this makes sense. Anyway, I was charmed. So I thought, yes, why not? I won't do field geology. I really will do spectroscopy. And it was sad, because I otherwise would have gone to work for Mac Rutherford. Anyway, but Roger lured me into MIT with this project that was to study lunar glasses. And we were able to do some of the first basic work on spectroscopy and oxidation state in lunar glasses. And of course, that gave me my roots in planetary science. But Roger was very much an advocate of being well-rounded and having breadth. So he encouraged me to do terrestrial projects too. I studied granites in the Boston Basin. I've written 15 papers on the metamorphic petrology of the state of Maine. Roger allowed me to take painting classes while I was at MIT, so I was at MIT for 3 days a week, and 2 days a week I was taking painting classes. And he, most importantly, left me with a lot of really good advice. And unlike a lot of the faculty members at MIT at the time, Roger believed that people were really important and that family came first, and that's a value that he instilled in me from very early on. And he was also a tremendous gentleman and a person of very high professionalism and very high standards, and I aspire to live up to those. But he also had some really sort of funny things that he would always tell me. One of them was never miss an opportunity to submit a proposal. Because in those days, we didn't have proposals deadlines the way we do now. And of course, this has traumatized me now, because now when a proposal deadline comes up, I freak out because I'm not submitting anything. Or sometimes I submit a lot of them. Roger also taught me that science should tell a story. I like to think that my papers and my proposals do exactly that. They tell a story. They start with the very basic information and they move to the more comprehensive and complicated topics. And he also instilled in me the need to always want to ask why something happens instead of just what. And I think that is the key to making lasting fundamental contributions to our science, because explaining the what is a very useful occupation, I think, but explaining why is the kind of information that persists. And then finally, Roger imbued in me the attitude that all spectroscopy is the same, and this, of course, has also served me well. You know, in the Roger Burns world, energy goes in, energy comes out, you get wiggly lines, and you can figure it out. And in fact, that's what I've spent my career doing. I left MIT to go to Caltech. I spent a year working with George Rossman, who was the other god of mineralogy. George also had a Carey 17 spectrophotometer, but he also had a lot of other different kinds of equipment. I learned all about XRF. I was in on the ground floor of calibrating modern XRF machines, and then I basically ground the fingertips off of 3 of my fingers, preparing doubly mounted, thin, polished sections. And George's advice to me was just simply quoted here: do good science, Darby, keep your nose clean, and people will respect you. That's what George said. By which he meant, don't get involved in politics, don't care what other people think, have courage in your conviction when it comes to science, and you'll do great. So Roger and George succeeded in turning me into a mineralogist. I love minerals. These are some of my favorites here. I could go around the room and ask you to tell me what these minerals are. I won't embarrass you all. But I worked on a bunch of really great minerals, and again, it's been it was really nice to be able to do the fundamental Mossbauer work on probably 20 or 30 different mineral groups. And some of those early papers are listed here. Just for fun, I put my favorite one, Crystal Chemistry of Babingtonite, which is the state mineral of Massachusetts. I also worked on a bunch of other minerals in all different kinds of geological provenances. So this is what I mean about the Roger Burns attitude of breadth. And at the time, I had no idea that working on samples from the upper mantle would come in handy later, but it did. And, you know, like serpentines, for example. I have probably the world's best collection of serpentine separates. Why? Because I worked with a guy that sampled them from all the mines. So it's funny how your career kind of goes around and around in circles, and the minerals that I have collected in all these projects over the years just keep returning to be important. But there have been some tough years in my life, too. I left Caltech and went to a job at the University of Oregon. And I think it's sufficient to say that nothing I ever learned at Wellesley or MIT or Caltech prepared me for the way I was treated there. Let's see. Within weeks of arriving there, I was sexually harassed by a senior faculty member. And I filed a complaint, and as I did so, I found out that he had been harassing the undergraduate women in the department for more than a decade. So all of us joined together. We filed a complaint. The individual had his hand slapped. He was not removed from the institution, but stayed there. And so luckily, his behavior stopped, and I sort of saved all the subsequent women at the University of Oregon, including my now dear friend Molly McCanta, from having to deal with that problem. But unfortunately, I couldn't save myself, and the retaliation was swift and almost career-ending. But I persevered, and I managed to get a job at Westchester University in Pennsylvania, which is a lovely community college. They teach 8 classes a year. I took my research program there, and I started over. And this was career-changing for me in a lot of ways. When I was at Oregon, I worked 7 days a week, probably 12 hours a day. And a lot of the students said things to me like, we really respect you, Darby, but we don't want to grow up to be like you. And that kind of shook me up. So I had some reevaluation of what life was supposed to be about. And I realized that when bad things happen to you, you have 2 choices. You can sort of fold your tent and go away, or you can fight back. And in my case, I decided to fight back. And I resolved at that point in my career that if it was ever in my power to make things better for especially other women in this field, that I would do it. And I am 100% confident that I have done that. So I'm not bitter. Thank you. I was helped out of my funk by a lot of the people on this page here. This is another copy of that picture. Those are, yes, I didn't realize those were so life-changing for you, Rachel. Janice Bishop, in particular, gets the credit for dragging me back into planetary science. At this point, I was kind of, I was rebuilding my career, let's put it that way. And Janice, I think you either called me or sent me an email and said, Darby, Roger Burns has died. We need somebody that can do Mossbauer spectroscopy and planetary science. Please come back. And Janice and Jerry Delaney down here, and all of these people, Carly met me at the first LPSC when I came back after a 10-year absence and gave me good advice. And I was dragged physically back into this field, and I'm so fortunate that this happened. I also started working on synchrotron radiation with some of these people, Tony Lanzarotti, Molly McCanta, and those also have been career-changing. And also, I'm happy to say that somehow in that weird way of life, when your career is not doing well, your personal life does well. So at this point, I reconnected with my then husband, Peter Crowley, and had 2 amazing kids. Peter is a real field geologist, and so we got to take the kids all over the U.S. And this is Lindy, and this is on the left is Lindy and Duncan at a dinosaur dig. They've also been to Yellowstone so many times that they complain when you even mention the word. Whoops. There we go. Oh, darn. Can I go back? Yes, there we go. This is Duncan and Lindy look like this now. I'm very proud of them. Duncan just graduated from Harvey Mudd College, and Lindy is going to be a senior at Wellesley College next year. So she's 4th generation, carrying the torch. Lindy's going to study she's studying politics, however. Duncan, on the other hand, has worked at JPL and is my mechanical engineer. So some kids do follow in their father's footsteps. But maybe the most important thing in my career, of course, has been my students. And I have to say, you know, there's no other good way of saying this than to borrow the line from Wicked, right? Because I knew these people, I have been changed for good, right? I learned as much from them as they do from me, I think. And this is just a small sampling of the students I've had over the years. I think I've had at least, this is not an exaggeration, at least 500 people work in my research lab over 35 years. And I've probably had, I think, something like 10,000 students in my classroom. And I consider that, as a woman and a scientist and a person who cares about setting a good example and training the future workforce in science, I consider that probably the most important accomplishment of my career, and it's nice to have that mentioned as part of the citation here. My lab has done a bunch of amazing things. You know, Roger Burns once said to me, Darby, when you change jobs, don't go for a place that you think will give you prestige. He said, you, Darby, should take your prestige to the institution. And so I've been able to do well by Mount Holyoke, I think. We actually built the calibration targets for the Curiosity rover at Mount Holyoke. Most people don't know that. The standards that we developed at Mount Holyoke are in use around the world for, if you've ever analyzed lithium or boron or beryllium in a geological sample, you use my standards. We have about 10,000 mineral standards in the lab that have been used for all kinds of creative purposes. And of course, about a decade ago, I got interested in libs. But as an example of the things that my students have done for me, I wanted to talk a little bit about this kid with the circle around his head. That's Marco Carmosino. This particular summer, I had a hodgepodge of people in the lab. I had somebody that was an elementary ed major. I had 2 chemistry majors, a computer science major, and an astronomy major, no geologists. And we hired Marco. You notice he's the only guy. We hired him because we needed somebody to make a website for us. And one day, sitting in the lab, Marco looked over at what Erica and Sam Peel were doing, which was fitting spectra ad nauseum, and he said, why are you doing that? And they said, well, you know, they proceeded to explain to Marco how you did spectroscopy. You looked at these peaks, and they all arose from fundamental absorptions, and then you fit them, and good things happen. And Marco said, that's a really terrible way to do that. And we said, what? Anyway, so Marco said, give me those data. So an hour later, Marco came up with a method that revolutionized X-ray absorption spectroscopy and basically made 400 papers obsolete. So what does that tell you? It tells you that students are amazing. And in some ways, I delight in working with undergraduate students because, you know, a brilliant person knows no age, right? Just because they're 19 years old or 18 years old when they start working for me does not mean that they can't make incredible scientific contributions. And so it's just been a delight to be able to work with undergraduates, I have to say. Oops. So Marco dragged me, again, kicking and screaming, this is what students do to you, into the field of machine learning, as was mentioned earlier. And now I have graduate students who do machine learning. These are 2 of them, Tommy Boucher and CJ Carey, and their advisor at UMass, Sridhar Mahadevan. There's a whole field that's called machine learning of spectroscopy that's called, oops. There we go. No, I missed one. There we go. It's called chemometrics. That's what we're doing here, folks. There's actually a journal called the Journal of Chemometrics. And it combines all these things. It uses, you know, machine learning to do all this cool stuff, and it's highly applicable to spectroscopy. And as an example of this, I'll show an example from XAS, X-ray absorption spectra. This is a kind of spectroscopy that you're probably not used to, so, but that's good because I won't offend anybody. So this type of spectroscopy was studied for years, and the way they did it was they looked at that little nub that occurs at 7110, maybe 7112, which is a 1s to ND transition, and they looked at the position of that particular spectral feature and they derived something from it. This was the dogma in this field, and again, this should remind you of some of the things that we do in other kinds of spectroscopy. They fit the peak, they made a calibration line, they put an R squared on it, and they said, aha, we have a brilliant way now of predicting percent ferric iron in this particular kind of spectroscopy. And then they realized that it was a little more complicated than this, so over the years a paper was developed. This is a paper by Wilkie, where they made it a little more difficult. So they knew these lines weren't straight, so they drew them crooked. And then they eyeballed where the little increments should be on all these plots, and they figured out a way to make this technique work on the basis, all on the basis of that little tiny feature in the pre-edge. So we got a hold of this problem, and we realized that it didn't really work very well. And we decided that maybe using machine learning would make it work better. And indeed it did. This is the problem that Marco solved in an hour. It turns out that if you look at the entire spectrum, not just the single bump, you actually get a much better result. And if I leave you with nothing else from today, if you remember this advice, using the entire spectrum is always better than using a small number of features. And we know this because we understand that there are important transitions that happen in mineral spectra, but there are also a lot of seemingly unimportant transitions that happen in mineral spectra. And when you combine all of them together, great things happen. So here's an example of two things that I wanted to show you. At the top are two models that show you a spectrum, and then those little wiggly red dashed lines on them are the PLS loadings and the coefficients. So those are the places where the multivariate analysis is telling you are the most important channels in these spectra. And you'll notice that there aren't any important channels where that little bump is. They're all in the other part of the spectrum. So this whole field was dragged down the wrong path by the fact that some early workers said all the information to be gained by this kind of spectroscopy is in that one feature. And this work shows very poignantly that all the information in the spectrum is actually in other places. So let this be a warning unto you who do spectroscopy, that sometimes our preconceived notions from fundamental spectroscopy are not always right. And then at the bottom is another method called the lasso. You can tune the lasso and you can say, hey, I've got this kind of spectroscopy, I want to predict this variable, and I'd like to know which 6 channels I want to put on my spacecraft to analyze that variable. And this will tell you in a very unambiguous manner. So there are ways of doing things that are, I think, better than the ways that I was taught to do in graduate school by using machine learning. There are also some other challenges that machine learning now allows us to address. This is one of them. It's called calibration transfer. You know, when I came up the pipeline, I was raised to think that the Carey 17 spectrophotometer at MIT was just like the one at Caltech, and that I could put those data side by side and they would look identical. But that was before we were putting instruments on other planets. So this is a slide that shows the LIBS spectrometer in my lab and the LIBS spectrometer on Mars, and those are spectra of the same exact calibration target in both places. And you'll notice that they are different. This is a problem that is pervasive in all types of spectroscopy, and as we get into more and more advanced things, particularly technologies that use lasers, lasers have a very hard time firing reproducibly all the time. And so calibration transfer is going to have to be something that becomes part of the planetary science toolkit in the coming decades. And we're working on it now, and the results will scare you. Another thing that concerns me about using these advanced multivariate analysis techniques is the fact that the databases we have are inadequate. And anybody in any field knows that his or her database has some challenges associated with it. And you may have encountered a situation like this. If you look at the spectrum in the upper left there, you'll see 3 spectra of the same mineral in the same database, and you can tell that they're not the same, right? And so machine learning gives you some options to be able to try to make these spectra all look the same, which is a really important thing, because when we're using databases, any kind of library, it's critically important to make our libraries all look the same. So we're working on a bunch of things like that. So finally, some sort of retrospective thoughts. So this plot kind of indicates what I do, right? I start with a mineral. This is a pyroxene. I think about the crystal structure. I look at the Tanabe-Sugano diagram, I think about all the possible transitions that could be there. I take the spectra and then I try to interpret rocks, because I am, after all, at heart, a geologist. But what's wrong with this picture is that we don't know diddly about mineral mixing. And here's the reason why. We have incredibly elegant solutions for mineral unmixing. The whole discipline of understanding mineral unmixing is fabulous. However, if you look in the databases, what you find is that all of the existing mineral mixtures in spectral libraries were done by weight, not by volume. And the problem with that is that when you do your mixtures by weight, you can't compare them. So 10% magnetite in a mixture with feldspar is not the same as 10% magnetite in a mixture with phthalite. So this is a huge problem in multiple types of spectroscopy. This big diagram that you see at the top happens to be a bunch of mineral mixtures that we've made in my lab by volume. And if anyone wants to borrow these for your type of spectroscopy, I will be happy to lend them. Because I think we need to do this so that we actually have decent databases with well-mixed, well-characterized minerals to play with. Let's see. So here, some sort of future remarks. What are the barriers to changing the way we do spectroscopy? I think at the moment there's too little overlap between our constituent communities. And it's very hard to get computer scientists to work with you. I had to write the proposals and fund the graduate students to get this to happen. And now that these graduate students have gotten their PhDs, they're making twice what I make. So they're not so inclined to come back and work for Darby for a postdoc, because I can't pay them enough to make this palatable to them. But it's going to be really important to our field. I've had a really steep learning curve trying to figure out how to understand all the machine learning stuff. And I too have been reluctant to move on from thinking about the 1 and 2 micron bands to trying to embrace the entire spectrum. But we have to go there if we want to extract all the available information out of these data. And we also have to have decent databases and libraries to do that, which means that we have to know what minerals they are. We have to have chemical compositions for them. We need to know their densities. And all of those things need work. Thank you, Sarah, for the PDART program, which is facilitating some of this work. And then finally, we have to take our heads out of the ground and recognize that there are instrumental differences between things that we have in the laboratory and things that we might have in another laboratory, such as on another planet. There we go. And here's what keeps Darby up at night. This is a picture from one of the books by my aunt, Natalie Babbitt. In reflecting on my career, I know I made a lot of mistakes, and sometimes I worry that it didn't make a difference, but then I hear a talk like Rachel's, and I think maybe it did. I worry a little bit about the switch of our planetary science workforce into centers where people are working full-time on research. And the reason I worry about that is that I wonder where the Marco Carmosinos will come from in this generation. My dear friends at the NASA centers are themselves siloed. They don't get to see this important cross-fertilization. And yet it gets harder and harder for those of us in academia who have so many other demands on our time to compete with the proposal writing machines and the full-time research capabilities of people in those other kinds of jobs. So I worry about that. I worry about planetary science being its own specialty. That's suddenly people are getting PhDs in planetary science. You didn't do that when I was a student. You got a PhD in geology or geochemistry and you applied it to planetary science. And I see that now. I see a lot of, again, these are things that keep me awake at night. I review proposals and read papers where people are very descriptive and they're not understanding why the phenomena that they're describing are happening. And that worries me. I worry about the difficulty of getting novel work funded as NASA becomes more application-based and less fundamental science-based, although thankfully NSF is still funding fundamental science. And then I worry about the work-life balance issue because I certainly struggled with that myself. And so in reflecting on my career, I can say that mistakes were made by me and to me, but it is possible to persevere, and as long as you have two kinds of passions. You have to have the passion that has your family and your friends and your colleagues supporting you, and then you have to have that intellectual passion up here that keeps you lying awake at night wondering where that bump came from and how am I going to interpret those data. And then I try to share with my students all of these things that Roger shared with me, that family always comes first, that people are the most important thing, that integrity is paramount, that asking why is the most important thing, that perspective is good. My students tell me, I ask them, what is the most common Darbyism? And they said, by far the most common Darbyism is, the world will not end if you don't finish blah, blah, blah today. But they also know the energy in, energy out. So to all of them and to all of you who have worked with me, which is probably half the people in this room, at least, I thank you very much for your attention. I have another cute slide. Thank you. Thank you very much. All right.
Thank you so much,
Aw.
Darby. Yeah, it was really
Thanks, Yvonne.
wonderful talk, and we're all very moved. Does anyone have a question for any of our speakers, but Darby in particular?
Am I the only one having these nightmares? Probably.
I have a question for Darby, but it's related to her talk at the beginning. The picture of your dad looks a lot like Rex Harrison.
Yes.
Is there, and that, he looks a lot.
No,
in fact,
there's no
the
relation.
movie-
My father was an incredibly handsome guy.
Okay, because he looks. Have you ever seen the movie The Ghost of Mrs. Muir?
Yes,
he looks
I have.
just like that.
Yes,
right?
it does.
So
Yes, it does.
I had to ask if that was.
Yeah, it does.
Okay. Yeah, so I'm not alone. All right, there you go. So, okay, so watch more Turner Classic Movies. You'll see what I mean.
That's great. Okay, well, thank you so much.
All right, thank you.
So I would like to now offer congratulations to all of our winners today, Darby, David Kring, Rachel Klima, and Barb Cohen, for their achievements and contributions. Each of these extremely dedicated individuals has helped advance our scientific understanding of the moon and other airless bodies, among a plethora of other things. Their outstanding research efforts are vital to the ambitious activities we hope to achieve in exploring the solar system with both robots and humans. I'd also like to thank Leslie Herlichson. Is she in the room? Leslie, can you stand up? They may have already left. There she is, okay. And the students that she brought with her, this is the Atom Science Club. Would you guys please stand up? They have been our microphone runners, and we have not acknowledged them yet, so thank you very much. And what you don't know is that all the homework they did ahead of time. They read every abstract. They tried to understand the terminology that they might not recognize, and they tried to use that as they were doing their job here. They did a great job. So I guess that is it for this session. I think that everybody has been uplifted by what we've heard here. So please join us in giving another round of applause for all of our award winners today and all of our students.